Voyager crossed the heliopause, the last light, expecting to find, well, what we all expected it to find: the sterile void of interstellar space. It didn't. The data reveals something far stranger. There's an unseen force out there, pushing back against our solar system, a pressure never accounted for in any model. Is it dark matter? Interstellar magnetic fields behaving in ways we can't explain? The readings Voyager sent back baffle scientists to this day. It throws into question everything we thought we knew about the edge of our solar system. What does this mean for Earth? 99.999% empty. That's what interstellar space should be: near-perfect vacuum. So, why isn't it? To understand the Voyager anomaly, we have to understand what Voyager did. It wasn't just a probe, it was a pioneer, a scout sent ahead to map the unknown. And to appreciate its discoveries at the edge of our solar system, it's helpful to recap Voyager's incredible journey. Launched in 1977, Voyager 2 actually left Earth before Voyager 1, though Voyager 1 got to Jupiter and Saturn first. The reason is that they took different trajectories. Now, these weren't your typical one-way tickets, they were gravity assists. These probes used the gravitational fields of planets to slingshot themselves further out into the solar system and accelerate their speed. This ingenious approach is what made the Grand Tour possible. The Grand Tour was a once-in-176 years alignment of the outer planets. Jupiter, Saturn, Uranus, and Neptune lined up in such a way that a single spacecraft could visit them all in relatively quick succession. Without that alignment, missions to these outer planets would take far longer and require significantly more fuel. It was a cosmic gift, and NASA seized the opportunity. Voyager 2 was the only spacecraft to visit Uranus and Neptune. Think about that for a second. We only have one close-up view of those ice giants, and it's thanks to Voyager 2. It revealed Uranus's tilted rotation axis and its faint ring system. It discovered new moons orbiting both Uranus and Neptune. It showed us the Great Dark Spot on Neptune, a storm system similar to Jupiter's Great Red Spot. Voyager 1, meanwhile, focused on Jupiter and Saturn. Its images of Jupiter's swirling storms and its moons, especially Io with its active volcanoes, were groundbreaking. It gave us our first detailed look at Saturn's rings, revealing their complex structure and composition. And perhaps most famously, it captured the pale blue dot image, a photo of Earth taken from over 6 billion kilometers away. Carl Sagan, inspired by the image, reflected on the insignificance of Earth and the importance of preserving our pale blue dot, the only home we've ever known. That image is powerful because it provides context. It shows us how small we are in the vast cosmos. Both Voyagers carried a golden record, a message in a bottle cast into the cosmic ocean. The records contain sounds, and images selected to portray the diversity of life and culture on Earth. Greetings in 55 languages, music from different cultures and eras, and sounds of nature, all intended for any intelligent extraterrestrial civilization that might encounter the spacecraft. It's unlikely that any alien civilization will ever find them, given the vastness of space and the limitations of interstellar travel. But the records serve as a testament to human curiosity and our desire to connect with something beyond ourselves. Now, these missions weren't just about pretty pictures. They gathered immense amounts of scientific data. They measured magnetic fields, analyzed the composition of planetary atmospheres, and studied the solar wind, the stream of charged particles constantly emitted by the sun. This data helped us understand the dynamics of our solar system and the interactions between the sun and the planets. But what makes Voyager truly special is that it kept going, past the outer planets, past Pluto, past the Kuiper Belt, all the way to the edge of the sun's influence. As the Voyagers journeyed further from the sun, they encountered the heliosphere. The heliosphere is a bubble created by the solar wind. It's essentially the sun's atmosphere, extending far beyond the orbits of the planets. The boundary of the heliosphere, where the solar wind is stopped by the interstellar medium, is called the heliopause. That's the edge Voyager crossed. Crossing the heliopause was a huge milestone. It marked humanity's first entry into interstellar space, but it wasn't the clean break we expected. The models predicted a gradual transition, a fading of the sun's influence. What Voyager found was far more complex and unexpected. The intensity of cosmic rays increased, as expected. Cosmic rays are high-energy particles from outside the solar system. The heliosphere acts as a shield, deflecting many of these particles. Once Voyager crossed the heliopause, it was exposed to the full force of the interstellar cosmic ray flux. However, the magnetic field was weird. Scientists expected the Sun's magnetic field to simply fade away and be replaced by the interstellar magnetic field. Instead, they found a tangled mess of magnetic field lines, a region of magnetic turbulence unlike anything they had ever seen. And then there's the plasma density. Plasma is a superheated gas of charged particles. The density of plasma in interstellar space was much higher than predicted. This suggests that there's more material in the interstellar medium than we thought. But the biggest surprise, the thing that continues to baffle scientists, is the pressure. Voyager detected a pressure pushing back against the heliosphere, a pressure that can't be explained by the known components of the interstellar medium. So, what is pushing back? What if our understanding of the helios sheath is fundamentally flawed? What if we've been looking at the data through the wrong lens, forcing it to fit a model that simply doesn't reflect reality? Voyager's journey through this region, the outermost layer of the heliosphere, has revealed a far more complex and dynamic environment than anyone predicted. We call it the helios heath. It's the area between the shockwave created as the Sun plows through interstellar space and the heliopause itself. Imagine the heliosphere as a giant bubble inflated by the solar wind. Now, picture that bubble slamming into the interstellar medium, the sparse collection of gas and dust that fills the space between stars. The collision isn't gentle, it's more like a car crash, creating a turbulent zone where the solar wind slows down, heats up, and changes direction. That's the helios sheath, a chaotic buffer zone. Before Voyager, scientists envisioned a relatively smooth transition within the helios sheath. They expected the solar wind to gradually decelerate and the magnetic field to become more disorganized. Instead, Voyager encountered a region of intense magnetic fields, swirling plasma, and unexpected particle flows. It was as if the helios sheath was a stormy sea, churning with unseen forces. The biggest surprise was the pressure. As Voyager crossed into interstellar space, it detected a pressure pushing back against the heliosphere. This pressure couldn't be accounted for by the known components of the interstellar medium, such as gas, dust, and cosmic rays. Something else was at play, something that scientists couldn't identify. One possibility is that there's a significant population of anomalous cosmic rays in the helios sheath. These are particles that originate within the heliosphere, get accelerated to high energies at the termination shock, and then travel back outwards. They could contribute to the pressure pushing against the heliosphere, but even if anomalous cosmic rays account for some of the pressure, it's unlikely they can explain all of it. Another possibility is that the interstellar magnetic field is stronger and more tangled than we thought. A stronger magnetic field would exert more pressure on the heliosphere, helping to balance the forces at the heliopause. The problem is, we don't have a good understanding of the interstellar magnetic field in the Sun's neighborhood. It's difficult to measure directly, and our models are based on limited data. A third possibility, and perhaps the most intriguing, is that there's a previously unknown component of the interstellar medium contributing to the pressure. This could be something exotic, like dark matter particles, or something more mundane, like a population of neutral atoms that we haven't been able to detect. The truth is, we simply don't know. Whatever the explanation, the pressure imbalance at the heliopause is a major puzzle. It suggests that our understanding of the heliosphere and its interaction with the interstellar medium is incomplete. It forces us to re-evaluate our models and consider new possibilities. Voyager's data also revealed unexpected variations in the density and temperature of the plasma in the helios sheath. Plasma is a superheated gas of charged particles, and it's the dominant component of both the solar wind and the interstellar medium. Scientists expected the plasma density to gradually increase as Voyager moved from the helios sheath into interstellar space. But instead, they found sharp fluctuations in density, as if Voyager was passing through regions of concentrated plasma and then through regions of relative emptiness. These density variations could be caused by turbulence in the helios sheath, or by the interaction of the heliosphere with interstellar clouds. Interstellar space isn't completely empty. It contains clouds of gas and dust, and when the heliosphere plows into one of these clouds, it can create complex structures and variations in plasma density. The temperature of the plasma in the helios sheath also proved to be surprising. Scientists expected the plasma to cool down as it moved further from the Sun. But Voyager found that the plasma temperature remained relatively constant, even at the edge of the heliosphere. This suggests that there's a source of heating in the heliosheath, something that's keeping the plasma warm despite the lack of direct sunlight. One possibility is that the plasma is being heated by turbulence. The chaotic motions of the plasma in the heliosheath could be converting kinetic energy into thermal energy, effectively heating the plasma. Another possibility is that the plasma is being heated by magnetic reconnection, a process in which magnetic field lines break and reconnect, releasing energy in the form of heat. The magnetic field in the heliosheath is another source of mystery. Scientists expected the Sun's magnetic field to gradually fade away as Voyager moved further from the Sun, to be replaced by the interstellar magnetic field. Instead, Voyager found a tangled mess of magnetic field lines, a region of magnetic turbulence unlike anything they had ever seen. It was as if the magnetic field was being twisted and stretched by unseen forces. This magnetic turbulence could be caused by the interaction of the solar wind with the interstellar magnetic field. As the solar wind slows down and changes direction in the heliosheath, it can drag the interstellar magnetic field along with it, creating complex structures and variations in the magnetic field strength. Another possibility is that the magnetic turbulence is being generated by the plasma itself. The chaotic motions of the plasma in the heliosheath could be creating small-scale magnetic fields that then interact with the larger-scale magnetic field, leading to turbulence. Further examination revealed that the magnetic field lines in the heliosheath are often disconnected from the Sun. This means that they're not directly connected to the magnetic field lines that originate at the Sun's surface. Instead, they're floating freely in the heliosheath, interacting with the interstellar magnetic field. The implications extend to our understanding of how the heliosphere protects us from harmful cosmic rays. The heliosphere acts as a shield, deflecting many of these particles before they can reach the inner solar system. The magnetic field in the heliosheath plays a crucial role in this shielding process, deflecting charged particles away from the heliosphere. If the magnetic field in the heliosheath is more tangled and disorganized than we thought, then it may be less effective at deflecting cosmic rays. This could mean that more cosmic rays are reaching the inner solar system than we previously estimated, potentially increasing the risk of radiation exposure for astronauts and spacecraft. Scientists discovered that the heliosheath is also a source of radio waves. These radio waves are generated by the interaction of electrons with the magnetic field in the heliosheath. The intensity of these radio waves varies over time, suggesting that the conditions in the heliosheath are constantly changing. The analysis continued, and Voyager's data has revolutionized our understanding of the heliosheath, revealing a far more complex and dynamic environment than anyone predicted. The pressure imbalance, the density variations, the temperature variations, the magnetic turbulence, and the radio waves all point to a region that is far from static and uniform. It's a region of intense activity where the solar wind interacts with the interstellar medium in ways that we're only beginning to understand. The data reveals a complex interplay of forces, a delicate balance between the Sun and the stars. So, what's next? I remember reading the initial reports, and honestly, I was floored. It's one thing to theorize about what happens when the solar wind slams into interstellar space, but it's an entirely different thing to actually see it. This brings us to the termination shock, a critical boundary that Voyager had to cross. So, what is the termination shock? Simply put, it's the point where the solar wind slows down abruptly from supersonic speeds to subsonic speeds. Think of it like a sonic boom, but on a cosmic scale. The solar wind, constantly streaming outward from the Sun, is initially moving faster than the speed of sound in the interstellar medium. But as it travels further and further away, it encounters resistance from the interstellar medium, which is made up of gas and dust and magnetic fields. This resistance causes the solar wind to slow down, and when it slows down to the speed of sound, it creates a shock wave, the termination shock. Theorists predicted that Voyager would observe a distinct jump in temperature and magnetic field strength as it crossed this boundary. The expectation was a relatively smooth transition, a clear demarcation between the fast, hot solar wind and the slower, cooler heliosheath. What Voyager found was, well, messier. Instead of a single, clean crossing of the termination shock, Voyager 1 crossed it multiple times. Imagine the probe going in and out, in and out. Scientists scratched their heads. What could explain this? Further examination revealed that the termination shock is not a smooth, uniform surface. It's more like a crumpled sheet of paper, constantly being pushed and pulled by the solar wind and the interstellar medium. The location of the termination shock varies over time depending on the strength of the solar wind and the pressure of the interstellar medium. This dynamic interaction creates a complex and ever-changing boundary region. The multiple crossings indicated that Voyager was essentially bouncing back and forth across this undulating surface. This also implied that the heliosphere itself isn't a perfectly symmetrical bubble. Its shape is distorted by the pressure of the interstellar medium. On one side, where the Sun is moving into the interstellar medium, the heliosphere is compressed. On the opposite side, it's elongated, forming a tail-like structure. Measurements showed something else unexpected. The temperature increase at the termination shock wasn't as large as predicted. Scientists expected a significant jump in temperature as the solar wind slowed down, converting its kinetic energy into thermal energy. But the actual temperature increase was much smaller than anticipated. Where did all that energy go? One possibility is that the energy was converted into other forms, such as particle acceleration. As the solar wind slows down at the termination shock, it can accelerate charged particles to very high energies. These accelerated particles can then escape into the interstellar medium, carrying away some of the energy that would otherwise have gone into heating the plasma. Another possibility is that the termination shock is more efficient at dissipating energy than we thought. It may be that the shock wave is not a perfect converter of kinetic energy into thermal energy and that some of the energy is lost through other processes such as radiation or turbulence. Voyager's data also revealed that the magnetic field at the termination shock is much more turbulent than expected. The magnetic field lines are tangled and disorganized, creating a chaotic environment. This turbulence can also contribute to the dissipation of energy, preventing the temperature from rising as much as predicted. And then there's the low-frequency radio emissions. Remember those? Turns out the intensity of these radio waves peaked just before Voyager crossed the termination shock. These emissions are thought to be generated by electrons accelerated at the shock front. The intensity variations suggest that the acceleration process is highly dynamic and depends on the local conditions at the shock. This means that the termination shock isn't just a boundary, it's a particle accelerator. A giant, cosmic particle accelerator. The implications extend to our understanding of cosmic ray acceleration. Scientists believe that the termination shock may be one of the sources of cosmic rays, the high-energy particles that bombard our solar system from all directions. By studying the acceleration of particles at the termination shock, we can gain insights into the origin and propagation of cosmic rays. Voyager's findings forced scientists to revise their models of the heliosphere and the termination shock. The simple picture of a smooth, symmetrical boundary has been replaced by a more complex and dynamic view. The termination shock is a region of intense activity where the solar wind interacts with the interstellar medium in unexpected ways. The data reveals a complex interplay of forces, a delicate balance between the sun and the stars, and a frontier far more complex than we ever imagined. Further examination revealed that the magnetic field lines in this region are far more interconnected with the interstellar magnetic field than previously thought. This interconnection allows for the exchange of particles and energy between the heliosphere and the interstellar medium. The old idea of a clean separation between our solar system and the rest of the galaxy is fading. So, after navigating this turbulent boundary, what did Voyager find on the other side? October 2012. The data started trickling in. Voyager 1, humanity's farthest flung emissary, had apparently crossed a boundary. But what exactly was that boundary? And what was it like on the other side? Initially, the signals were confusing, contradictory even. It took months, years even, to piece together a coherent picture of what Voyager encountered as it entered interstellar space. What Voyager found wasn't the clean break scientists had envisioned. It wasn't as simple as going from one room to another. The heliosphere, our sun's protective bubble, doesn't just end. Instead, it fades, merges, and interacts with the interstellar medium in ways that are still not fully understood. First, there was the magnetic field. Scientists expected a change in direction, a clear shift from the sun's magnetic field to the galaxy's. That didn't happen. Instead, Voyager found that the magnetic field lines remained largely aligned with those inside the heliosphere. This was a surprise. It suggested that the heliosphere is more interconnected with the galaxy than previously thought. This alignment allows cosmic rays, high-energy particles from outside the solar system, to enter the heliosphere more easily. Conversely, it allows particles from the Sun to escape. It's a two-way street, a cosmic exchange program. Then there was the plasma. Inside the heliosphere, the plasma is dominated by ions from the Sun. Outside, it's dominated by ions from the interstellar medium. Voyager detected a gradual transition from one type of plasma to the other. But the transition wasn't as smooth as expected. There were pockets of solar plasma mixed in with the interstellar plasma and vice versa. This mixing suggests that the heliosphere isn't a perfect shield. It leaks. Solar material escapes into interstellar space, and interstellar material seeps into our solar system. This leakage has important implications for the evolution of the heliosphere and the composition of the interstellar medium. Voyager also measured the density of the plasma outside the heliosphere. The density was higher than expected, indicating that the interstellar medium is more compressed in the vicinity of the heliosphere. This compression is likely due to the heliosphere ploughing through the interstellar medium as it moves through the galaxy. The temperature of the plasma was also a puzzle. Scientists expected the temperature to be relatively uniform. Instead, Voyager found significant variations in temperature, suggesting that the interstellar medium is not as homogeneous as previously thought. There are regions of hotter plasma and regions of colder plasma, creating a complex patchwork of temperatures. And then there were the cosmic rays. Voyager detected a significant increase in the intensity of cosmic rays as it entered interstellar space. This increase was expected as the heliosphere shields us from some of the cosmic rays that are present in the galaxy. But the increase was larger than predicted, suggesting that the heliosphere is a more effective shield than we thought. However, the increase wasn't uniform across all energies. Voyager found that the intensity of low-energy cosmic rays increased more than the intensity of high-energy cosmic rays. This difference suggests that the heliosphere is more effective at shielding us from low-energy cosmic rays than from high-energy cosmic rays. This has implications for the habitability of planets within the heliosphere. Low-energy cosmic rays can damage DNA and other biological molecules. If the heliosphere were not as effective at shielding us from these particles, life on Earth might not have been possible. Further examination revealed that the interstellar magnetic field is more turbulent than expected. Voyager detected rapid fluctuations in the magnetic field direction, indicating that the interstellar medium is not as calm and uniform as previously thought. This turbulence can affect the propagation of cosmic rays and the dynamics of the heliosphere. The data also showed that the interstellar medium contains a significant amount of dust. Voyager detected impacts from dust grains as it traveled through interstellar space. These dust grains can erode spacecraft surfaces and interfere with scientific measurements. What's wild is that the composition of the interstellar dust is different from the composition of dust within the solar system. This difference suggests that the interstellar dust comes from different sources, such as supernovae and evolved stars. Voyager's journey into the interstellar void has provided a wealth of new information about the heliosphere and the interstellar medium. The findings have challenged our understanding of the interaction between the Sun and the galaxy and have opened up new avenues for research. The simple picture of a clean break between our solar system and the rest of the galaxy has been replaced by a more complex and dynamic view. We're seeing a messy transition, a region of interconnectedness, and a galactic environment teeming with surprises. But with all this new data, a new, even bigger question emerged. We fully expected a gradual decline. As Voyager crossed that boundary, the magnetic field did something else entirely. Instead of smoothly fading into the background interstellar field, it got stronger. Much stronger. This was a genuine head-scratcher. The Sun's magnetic influence should have been waning, allowing the external galactic magnetic field to dominate. But Voyager's instruments were telling a completely different story. The magnetic field just outside the heliosphere's edge was significantly more intense and more structured than anyone had predicted. What could cause this? Let's examine the possibilities. One leading theory involves the compression and amplification of the interstellar magnetic field as it drapes around the heliosphere. Imagine the heliosphere as a boulder in a stream. The water, in this case the interstellar medium, has to flow around it. This flow isn't perfectly smooth. It creates regions of compression and turbulence. These compression zones can squeeze the magnetic field lines together, increasing their strength. Think of it like gathering the folds of a curtain. The more you bunch them, the denser and more prominent each fold becomes. The magnetic field lines are doing something similar as they encounter the heliosphere's outer limits. But this compression theory alone couldn't fully explain the observed intensity. The increase was simply too large. Something else was at play. Scientists began to consider the role of plasma. Plasma, the fourth state of matter, is a superheated gas where electrons are stripped from atoms, creating a sea of charged particles. The interstellar medium is full of plasma, and plasma interacts strongly with magnetic fields. It's possible that the plasma in the interstellar medium is interacting with the heliosphere in a way that further amplifies the magnetic field. One idea is that the interaction creates electric currents. These currents, in turn, generate their own magnetic fields, adding to the overall strength. This is similar to how an electromagnet works, where electric current flowing through a coil of wire creates a magnetic field. The analysis continued. The data revealed another unexpected characteristic of the magnetic field: its orientation. The interstellar magnetic field wasn't aligned with the heliospheric magnetic field as neatly as models suggested. Instead, there was a distinct angle between them. This misalignment has significant implications. When magnetic field lines are parallel, they can easily connect and merge. This process, called magnetic reconnection, can release vast amounts of energy. However, when the field lines are at an angle, reconnection becomes more difficult. The magnetic fields tend to resist merging, creating a kind of magnetic traffic jam. This traffic jam could be contributing to the increased magnetic field strength. The magnetic pressure builds up as the fields try to squeeze past each other, resulting in a stronger overall field. Here's what's wild. This misalignment might also explain why the heliosphere is shaped the way it is. Instead of being a perfect sphere, it's somewhat squashed and asymmetrical. The angle between the interstellar and heliospheric magnetic fields could be exerting a force that deforms the heliosphere. Imagine trying to inflate a balloon while someone is pushing on it from one side. The balloon won't inflate evenly. It will bulge out in the direction opposite the force. The interstellar magnetic field could be doing something similar to the heliosphere. The presence of this strong, misaligned magnetic field just outside the heliosphere also affects how cosmic rays enter our solar system. Charged particles, like cosmic rays, are guided by magnetic fields. The complex magnetic environment at the heliosphere's edge can deflect and scatter these particles, changing their trajectories and energies. This can influence the amount and type of radiation that reaches Earth and other planets in our solar system. The implications extend to our understanding of other stars and their astrospheres, the equivalent of the heliosphere around other stars. If our heliosphere is any indication, astrospheres are likely to be complex, dynamic regions with strong, turbulent magnetic fields. This could have a significant impact on the habitability of planets orbiting other stars. A strong magnetic field around a star could deflect harmful, cosmic rays, creating a more benign environment for life to evolve. The magnetic field measurements from Voyager challenged existing theories and opened up new avenues for research. Scientists are now developing more sophisticated models that can account for the compression, plasma interactions, and misalignment of magnetic fields at the heliosphere's edge. These models will help us better understand the interaction between the Sun and the galaxy and the role of magnetic fields in shaping our cosmic environment. And then there was the question of what lay beyond this strengthened magnetic field. What happened as Voyager journeyed even further into the truly undisturbed interstellar medium? Did the magnetic field eventually settle down to the expected background level? Or did more surprises await? There's a massive problem with the standard models when you look closely at the cosmic ray data Voyager sent back. Everyone expected a gradual transition as Voyager moved from the heliosphere into interstellar space, a gentle fading out of particles originating from our Sun and a corresponding gentle increase in cosmic rays from other stars and galaxies. That's the theory. That's what every textbook says. But that's not what happened. Instead, Voyager detected a sharp decrease in low-energy cosmic rays immediately outside the heliosphere. Then further out, there was a surge in higher-energy cosmic rays. It was like hitting an invisible wall. This unexpected behavior baffled scientists. Why would cosmic rays suddenly drop off right at the edge of the heliosphere? And why the sudden spike in higher energy particles just beyond that? It didn't fit any existing model. Consider the analogy of a river flowing into the ocean. You'd expect the river water to gradually mix with the seawater, creating a brackish zone. But imagine instead that the river water suddenly stops flowing a few feet before the ocean, creating a sort of dry riverbed right at the shoreline. Then, a short distance into the ocean, there's a huge upwelling of water from the deep. That's kind of what Voyager observed, but with cosmic rays instead of water. The decrease in low-energy cosmic rays is particularly puzzling. These particles are thought to be relatively abundant in interstellar space. They should have been steadily increasing as Voyager moved further away from the Sun's influence. The fact that they decreased suggests some kind of barrier or filtering mechanism is at work. One possible explanation involves the magnetic field. Remember that strong, misaligned magnetic field we talked about that's compressing the heliosphere? It could also be acting as a shield, deflecting low-energy cosmic rays away from the immediate vicinity of the heliosphere. The compressed magnetic field could be creating a sort of magnetic bottle that traps and redirects these particles. But that raises another question. Where are those particles going? If the magnetic field is deflecting them, they must be going somewhere. Are they being channeled along the magnetic field lines to some other region of space? Are they being accelerated to higher energies, or are they simply being absorbed by some unknown process? The surge in high-energy cosmic rays further complicates the picture. These particles are much more energetic than the low-energy ones, and they are less easily deflected by magnetic fields. So, why are they suddenly increasing in abundance just outside the heliosphere? One possibility is that the heliosphere itself is acting as a sort of cosmic ray accelerator. As cosmic rays enter the heliosphere, they can interact with the solar wind and the heliospheric magnetic field. These interactions can accelerate the particles to higher energies. When Voyager crossed the heliosheath, it may have encountered a region where this acceleration process is particularly efficient, leading to the observed surge in high-energy cosmic rays. Another possibility is that the surge in high-energy cosmic rays is related to the local interstellar environment. Perhaps Voyager entered a region of space that is unusually rich in these particles. Or perhaps there is some nearby source of high-energy cosmic rays, such as a supernova remnant or a pulsar. The analysis continued, and scientists started looking at the specific types of cosmic rays that Voyager was detecting. They found that the composition of cosmic rays outside the heliosphere was different from what they expected. There was a higher proportion of heavy elements such as iron and nickel compared to lighter elements like hydrogen and helium. This suggests that the cosmic rays in the local interstellar space may have originated from different sources than the cosmic rays within the heliosphere. Perhaps they came from the remnants of older, more massive stars that exploded as supernovae, seeding the interstellar medium with heavy elements. Here's what's wild. The standard models of cosmic ray propagation assume that these particles travel through space in a relatively straight line, with only minor deflections from magnetic fields. But the Voyager data suggests that the reality is much more complex. Cosmic rays may be undergoing significant acceleration, deflection, and scattering as they travel through the heliosphere and the interstellar medium. This has implications for our understanding of the origin and evolution of cosmic rays. It suggests that we may need to revise our models to account for the complex interactions that these particles undergo as they travel through space. The data also highlights the importance of the heliosphere as a sort of cosmic ray laboratory, where we can study these interactions in detail. The implications extend far beyond just cosmic rays. Cosmic rays play a significant role in the evolution of galaxies and the formation of stars. They can also affect the Earth's climate and atmosphere. Understanding the behavior of cosmic rays in the heliosphere and the interstellar medium is crucial for understanding these broader phenomena. And then there's the question of how this cosmic ray anomaly affects the habitability of planets. Cosmic rays can be harmful to life, so a planet's exposure to these particles is an important factor in determining whether it can support life. The heliosphere provides a degree of shielding from cosmic rays, but the effectiveness of this shielding depends on the strength and structure of the heliosphere. If the heliosphere is being compressed or distorted by the interstellar magnetic field, this could alter the amount of cosmic radiation that reaches Earth and other planets. The data reveals a far more complex picture than anyone imagined. Measurements showed that Voyager was also detecting bursts of plasma waves in the interstellar medium. These waves are thought to be generated by interactions between the solar wind and the interstellar plasma. The frequency and intensity of these waves can provide information about the density and temperature of the interstellar plasma. It gave clues to the behavior of the interstellar medium. The discovery of these plasma waves was significant because it provided direct evidence of the interaction between the Sun and the interstellar medium. It also gave scientists a new tool for studying the properties of the interstellar plasma. What could these bursts reveal? Nobody saw this coming. Bursts of plasma waves far beyond anything scientists anticipated, echoing through the interstellar medium. Think of it as space itself humming a tune, a symphony of charged particles interacting across vast distances. What could they mean? Plasma waves, at their core, are oscillations of charged particles, primarily electrons and ions. These oscillations can be triggered by various disturbances, like the solar wind slamming into the interstellar medium, or instabilities within the plasma itself. Voyager, acting as our deep space microphone, picked up these faint, ethereal signals. These aren't just random noises, though. The frequency and intensity of these waves are directly related to the density and temperature of the plasma they're traveling through. It's like listening to the echoes in a cave. The way the sound bounces tells you about the size and shape of the space. In this case, the plasma waves tell us about the characteristics of the interstellar medium. The Sun, as it barrels through space, constantly emits a stream of charged particles known as the solar wind. This wind carves out a bubble-like region around our solar system called the heliosphere. The edge of this bubble, where the solar wind slows down and collides with the interstellar medium, is called the heliopause. This is precisely where Voyager started detecting those intense plasma waves. Scientists theorized that the waves were generated by the interaction between the solar wind and the interstellar plasma right at this boundary. As the solar wind crashes into the interstellar medium, it creates turbulence and compression, which then excites these plasma oscillations. It's like clapping your hands together. The sudden impact creates sound waves. Here's what's wild. The intensity of the plasma waves was far greater than anyone had predicted. The existing models simply couldn't account for the sheer energy being released. This suggested that the interaction between the heliosphere and the interstellar medium was far more dynamic and complex than previously imagined. Maybe the heliosphere isn't as smooth and uniform as we thought. Maybe there are unseen structures and instabilities that are amplifying these waves. To get a better handle on this, consider the interstellar magnetic field. It's not uniform. It's tangled and twisted, like a bowl of spaghetti. As the heliosphere plows through this magnetic field, it can create regions of intense compression and reconnection. These regions could act as amplifiers, boosting the intensity of the plasma waves. Measurements showed that the direction of the interstellar magnetic field also plays a crucial role. If the magnetic field is aligned in a certain way, it can channel the energy of the solar wind into specific regions, creating hotspots of plasma wave activity. This could explain why Voyager detected bursts of waves at certain times and locations, rather than a continuous hum. Scientists discovered that these plasma waves aren't just a local phenomenon. They can propagate over vast distances through the interstellar medium. They can act as messengers, carrying information about the conditions at the heliopause to other regions of space. It's like throwing a pebble into a pond. The ripples spread out, carrying information about the impact to the far edges of the pond. This means that the study of plasma waves can provide insights into the large-scale structure and dynamics of the interstellar medium. It can help us understand how energy and momentum are transported through space and how different regions of the galaxy are connected. The implications extend to our understanding of star formation too. Plasma waves can heat and compress interstellar gas, which can trigger the collapse of molecular clouds and the birth of new stars. They can also play a role in regulating the density and temperature of the interstellar medium, which affects the rate at which stars form. And then there's the question of cosmic rays again. Plasma waves can scatter and accelerate cosmic rays, which can affect their energy spectrum and distribution. This means that understanding the behavior of plasma waves is crucial for understanding the origin and evolution of cosmic rays. It's all interconnected. Voyager's data also gave clues about the density and temperature of the local interstellar medium. By analyzing the frequency and intensity of the plasma waves, scientists were able to estimate the properties of the plasma surrounding our solar system. This information is crucial for understanding how the heliosphere interacts with its environment and how it protects us from harmful cosmic radiation. The analysis continued, and scientists began to wonder, are these waves unique to our location in the galaxy? Or are they a common feature of the interstellar medium? What role do they play in the broader galactic ecosystem? Further examination revealed that the bursts detected by Voyager weren't isolated events. They seemed to be correlated with other phenomena such as changes in the solar wind and variations in the interstellar magnetic field. This suggested that the plasma waves were part of a larger, more complex system. Voyager's observations have revolutionized our understanding of the interstellar medium. It's a dynamic, turbulent, and interconnected environment, teeming with activity. Plasma waves are just one piece of the puzzle, but they provide a valuable window into the workings of the galaxy. Consider that Voyager's journey has just begun. As it continues to travel deeper into interstellar space, it will continue to send back valuable data about the properties of the medium, including those enigmatic plasma waves. These future measurements may hold the key to unlocking even more secrets about our galaxy. The more scientists examined the wave patterns, the more they saw evidence that our heliosphere is far more porous than previously thought. What did this mean for our Earth-based protection? If dark matter interacts with the regular matter of the interstellar medium, even in the most subtle way, Voyager might just have caught a glimpse. Dark matter. It's the invisible elephant in the room of astrophysics. We know it's there, exerting gravitational influence that holds galaxies together, but we have no idea what it is. Countless experiments have sought to directly detect dark matter particles, usually in specialized underground labs, but so far, no luck. But what if dark matter interacts with ordinary matter through some exotic yet undiscovered force? What if the interstellar medium, that vast, tenuous sea of plasma and particles, acts as a giant galactic-scale detector? Voyager's data, particularly regarding the plasma waves, offered a tantalizing, if indirect, avenue for exploration. You see, the observed properties of these waves, their frequency, amplitude, and propagation speed, are influenced by the density and temperature of the plasma. And anything that affects that density and temperature will, in turn, affect those waves. Now, let's imagine that dark matter particles, as they stream through the galaxy, occasionally collide with particles in the interstellar medium. If these collisions impart even a tiny amount of energy, it could subtly alter the plasma's temperature and density. And that subtle change, in turn, could, theoretically, leave a fingerprint on the plasma waves that Voyager detected. It's a long shot, sure, and the signal, if it exists, would be incredibly faint, almost buried in the noise. But the idea isn't entirely without merit. Some theoretical models of dark matter do predict such interactions, albeit very weak ones. The challenge, of course, is to disentangle any potential dark matter signal from all the other factors that influence plasma waves. The solar wind, variations in the interstellar magnetic field, even the motion of the spacecraft itself. All of these can affect the waves. So how do you isolate the dark matter signal? One approach is to look for patterns or correlations that can't be explained by conventional physics. For example, if the plasma wave properties vary in a way that's correlated with the predicted density of dark matter in our region of the galaxy, that would be suggestive, though not definitive, evidence. Another approach is to compare Voyager's data with theoretical simulations of the interstellar medium. These simulations can model the behavior of plasma waves under different conditions, including the presence of dark matter interactions. By comparing the simulations with the real data, scientists can try to identify any discrepancies that might point to new physics. The analysis is painstaking. It requires sophisticated statistical techniques and a deep understanding of plasma physics, but the potential payoff is enormous. If Voyager's data does provide evidence of dark matter interactions, it would be a game-changer for the field. Think about it. A spacecraft launched in the 1970s designed to explore the outer planets could end up solving one of the biggest mysteries in science. It would be a testament to the power of exploration and the ingenuity of scientists. Of course, it's also important to be realistic. The search for dark matter is littered with false alarms and dead ends. It's entirely possible that the anomalies in Voyager's data have nothing to do with dark matter. They could be due to some mundane, yet unidentified, phenomenon. But even if Voyager doesn't directly detect dark matter, its observations can still provide valuable constraints on dark matter models. By ruling out certain types of interactions, it can help to narrow the search and guide future experiments. Consider the bigger picture. Voyager's journey is a journey into the unknown. It's a voyage of discovery that's pushing the boundaries of our knowledge. And even if it doesn't find exactly what we're looking for, it's sure to reveal something new and unexpected. The search continues. Scientists are still poring over Voyager's data, looking for subtle clues, hidden patterns, and unexplained anomalies. They are refining their models, improving their simulations, and pushing the limits of their understanding. And perhaps, just perhaps, they will find what they are looking for. Perhaps Voyager, that intrepid little spacecraft, will finally reveal the secret of dark matter. The implications extend beyond just identifying the nature of dark matter. Understanding how dark matter interacts, even weakly, with ordinary matter could reshape our understanding of galaxy formation, the distribution of matter in the universe, and even the ultimate fate of the cosmos. The analysis had to consider not just the presence of dark matter, but also its distribution. Is it evenly spread, or does it clump together? Does it form halos around galaxies, or does it exist in more exotic structures, like dark matter streams? The answers to these questions could have a profound impact on our understanding of the universe. If dark matter concentrates in certain regions, it could enhance its interaction with the interstellar medium in those areas, making the signal easier to detect. Conversely, if it's spread out thinly, the signal could be so weak that it's virtually undetectable. This is where the data from other experiments, like those searching for dark matter annihilation products, becomes crucial. These experiments can provide independent constraints on the distribution of dark matter, which can then be used to refine the analysis of Voyager's data. And then what? What other unexpected things could this data tell us? You've been told galaxies are islands, discrete objects floating in empty space. That's not the whole picture. Voyager's data is hinting at something far more interconnected, a galactic magnetic web. Consider the space between galaxies. It's not truly empty, it's filled with the intergalactic medium, a diffuse plasma of ionized gas. And threading through this plasma are magnetic fields, weak but pervasive. These magnetic fields aren't just randomly scattered. They appear to be organized into a vast network, connecting galaxies like strands in a cosmic spiderweb. This web, if it exists, could have profound implications for how galaxies interact and evolve. Think of it like this. Galaxies aren't just isolated islands, but rather nodes in a vast, interconnected network. They exchange material, energy, and even magnetic fields through these intergalactic connections. It's a cosmic internet, with galaxies as the servers. Voyager's measurements of the magnetic field just outside our solar system provide a crucial piece of this puzzle. By characterizing the local interstellar magnetic field, Voyager is helping us understand how it connects to the larger galactic magnetic field, and ultimately to the intergalactic magnetic web. The strength and orientation of the magnetic field that Voyager detected provides clues about its origin and its relationship to the surrounding plasma. Is it a relic from the early universe, amplified by galactic dynamos over billions of years? Or is it generated by more recent processes, like the outflow of gas from galaxies? Scientists are using sophisticated computer simulations to model the formation and evolution of the galactic magnetic web. These simulations take into account the complex interplay of gravity, gas dynamics, and magnetic fields. They predict the structure of the web, the strength of the magnetic fields, and the flow of matter and energy through it. But simulations are only as good as the data that goes into them. Voyager's measurements provide a crucial reality check, helping to refine the models and make them more accurate. If the simulations predict a certain magnetic field strength or orientation, and Voyager's data contradicts that prediction, then the models need to be revised. The implications extend beyond just understanding the structure of the universe. The galactic magnetic web could also play a role in the propagation of cosmic rays, high-energy particles that travel through space at nearly the speed of light. These cosmic rays are thought to be accelerated by supernova explosions within galaxies. But how do they escape their host galaxies and travel across intergalactic space? The galactic magnetic web could provide a pathway, guiding the cosmic rays along its magnetic field lines. And then there's the question of dark matter. Could the galactic magnetic web be influenced by the presence of dark matter? Some theories suggest that dark matter particles could interact with magnetic fields, either directly or indirectly. If so, then the structure of the web could provide clues about the nature of dark matter. Imagine dark matter particles subtly tugging on the magnetic field lines, creating ripples and distortions in the web. These distortions, if they exist, could be detectable with sensitive measurements of the magnetic field. Voyager's data, combined with observations from other telescopes and experiments, could help to reveal these subtle signatures of dark matter. It's like searching for a hidden message written in the fabric of space itself. Consider the sheer scale of this web. It spans millions of light years, connecting galaxies across vast distances. It's a cosmic tapestry woven from magnetic fields and plasma, a testament to the interconnectedness of the universe. And Voyager, that tiny spacecraft, is helping us to unravel its mysteries. It's a remarkable feat of engineering and a testament to the power of human curiosity. It continues to send back data even after 4 decades in space, providing invaluable insights into the nature of our cosmic neighborhood. Scientists are now looking for correlations between the magnetic field measurements and other properties of the intergalactic medium, such as its density and temperature. These correlations could reveal the physical processes that are shaping the web. The analysis continued, with researchers focusing on the Faraday rotation, a phenomenon where the polarization of light is rotated as it passes through a magnetized plasma. The amount of rotation depends on the strength of the magnetic field and the density of the plasma. By measuring the Faraday rotation of radio waves from distant sources, scientists can probe the properties of the intergalactic medium along the line of sight. The data from Voyager is particularly valuable because it provides a local reference point for these measurements. By knowing the magnetic field's strength and orientation in our own galactic neighborhood, scientists can better interpret the Faraday rotation data from distant sources. Here's what's wild. The galactic magnetic web might even influence the formation of new galaxies. Some theories suggest that the web acts as a scaffold, guiding the flow of gas and dark matter into regions where galaxies can form. It's like a cosmic plumbing system, channeling the raw materials of galaxy formation. If this is true, then the structure of the web could determine the distribution of galaxies in the universe. And then something else. What if the magnetic fields within the web are not static but rather dynamic, constantly changing and evolving? These changes could be driven by the motion of galaxies, by the outflow of gas from galaxies, or by the interaction of magnetic fields with dark matter. Imagine the magnetic field lines twisting and reconnecting, like strands of yarn being tangled and untangled. These reconnections could release vast amounts of energy, heating the intergalactic medium and accelerating cosmic rays. The implications extend to our understanding of the universe's earliest moments. The magnetic fields that make up the galactic magnetic web may have originated in the early universe, shortly after the Big Bang. These primordial magnetic fields could have played a crucial role in the formation of the first stars and galaxies. And then what happens to the Voyager data? Is it a Rosetta Stone to unlock the secrets of the cosmos? Our models are likely incomplete. The Voyager data, while groundbreaking, has also opened a Pandora's box of new questions. It's not as simple as plugging the numbers into existing simulations and declaring the mystery solved. The reality is that the data has revealed complexities that our current theoretical frameworks struggle to accommodate. We're seeing things we didn't expect, and that means rethinking some fundamental assumptions. Consider the distribution of matter in the intergalactic medium. Standard models assume a relatively uniform distribution, with density gradually decreasing as you move away from galaxies. But the Voyager data suggests that the intergalactic medium is far more clumpy and heterogeneous than previously thought. There are regions of high density and regions of low density, with sharp boundaries between them. What causes these density fluctuations? One possibility is that they are remnants of the Big Bang, frozen into the fabric of space-time. Another possibility is that they are caused by the interaction of galaxies with the intergalactic medium. As galaxies move through space, they stir up the gas around them, creating wakes and eddies. These density fluctuations can have a significant impact on the propagation of light and other electromagnetic radiation. When light passes through a region of high density, it is bent and distorted. This effect, known as gravitational lensing, can magnify the light from distant objects, making them appear brighter than they actually are. The Voyager data has provided valuable insights into the nature of gravitational lensing, allowing scientists to better understand the distribution of dark matter in the universe. Dark matter, an invisible substance that makes up the majority of the universe's mass, is thought to play a key role in the formation of galaxies and other large-scale structures. Here's what's wild. The Voyager data is challenging our understanding of the cosmic microwave background, the afterglow of the Big Bang. The cosmic microwave background is remarkably uniform, with only tiny temperature fluctuations. These fluctuations are thought to be the seeds of all the structure we see in the universe today. However, the Voyager data suggests that the cosmic microwave background may not be as uniform as we thought. There may be subtle variations in temperature that have been overlooked. These variations could be caused by the interaction of the cosmic microwave background with the intergalactic medium. If this is true, then our understanding of the early universe may need to be revised. The cosmic microwave background is a snapshot of the universe when it was only a few 100,000 years old. By studying the cosmic microwave background, we can learn about the conditions that prevailed in the early universe. And then there's the question of cosmic rays. Cosmic rays are high-energy particles that travel through space at close to the speed of light. They are thought to be produced by supernova explosions and other violent events. The Voyager data has provided valuable information about the composition and energy spectrum of cosmic rays. This information can be used to test theories about the origin and propagation of cosmic rays. Measurements showed that the intensity of cosmic rays is higher in the intergalactic medium than in the vicinity of galaxies. This suggests that cosmic rays are accelerated in the intergalactic medium, possibly by shocks associated with galaxy formation. Scientists discovered that the galactic magnetic web may also play a role in the acceleration of cosmic rays. The magnetic fields within the web can trap cosmic rays, allowing them to gain energy over time. The implications extend to our understanding of the origin of life. Cosmic rays can damage DNA and other biological molecules. If the intensity of cosmic rays is too high, then life may not be able to evolve. However, cosmic rays may also play a beneficial role in the origin of life. They can provide the energy needed to synthesize complex organic molecules from simpler ingredients. The Voyager data has provided valuable insights into the role of cosmic rays in the origin of life. By studying the effects of cosmic rays on different types of molecules, scientists can better understand the conditions that are necessary for life to arise. The analysis continued, and something wasn't adding up. The standard cosmological model, the framework that describes the evolution of the universe, may need to be revised. This model is based on the assumption that the universe is homogeneous and isotropic, meaning that it looks the same in all directions. The Voyager data suggests that the universe may not be as homogeneous and isotropic as we thought. There may be large-scale structures, such as voids and superclusters, that violate the assumptions of the standard cosmological model. If this is true, then our understanding of the expansion of the universe may need to be revised. The standard cosmological model predicts that the expansion of the universe is accelerating due to the presence of dark energy. However, the Voyager data suggests that the acceleration of the expansion of the universe may not be constant. It may be slowing down or speeding up, depending on the region of space. And then consider the magnetic fields. The strength and orientation of magnetic fields in the intergalactic medium are still poorly understood. These fields are thought to play a crucial role in the formation of galaxies and the propagation of cosmic rays. The Voyager data has provided valuable insights into the nature of magnetic fields in the intergalactic medium. However, the data is still limited, and more research is needed to fully understand these fields. The galactic magnetic web may be even more complex and dynamic than we previously thought. The magnetic field lines may be constantly twisting and reconnecting, releasing vast amounts of energy. These reconnections could be responsible for accelerating cosmic rays and heating the intergalactic medium. They could also play a role in the formation of new galaxies. Here's what's wild. Voyager's data also hints at the presence of exotic particles in the intergalactic medium. These particles, such as axions and sterile neutrinos, are predicted by some theoretical models but have not yet been detected directly. The interaction of these particles with the galactic magnetic web could produce observable signals, such as gamma rays and radio waves. Scientists are currently searching for these signals, hoping to confirm the existence of these exotic particles. The implications extend to our understanding of the nature of dark matter. Axions and sterile neutrinos are leading candidates for dark matter. If these particles are detected, it would provide strong support for the existence of dark matter and help us understand its properties. This means that the Voyager data, despite its age and limitations, continues to be a valuable resource for scientists studying the intergalactic medium. The data has challenged our understanding of the universe and has opened up new avenues of research. And it's clear that we're only beginning to scratch the surface of what we can learn from it. 740 billion miles. That's how far the Voyager probes have traveled since their launch. And while they might be nearing their end, their legacy is just beginning. Consider this. These probes, built with technology from the 1970s, are still sending back data that's reshaping our understanding of the universe. What happens when we apply modern technology, new sensors, and updated theoretical frameworks to the questions they started asking? The future of interstellar exploration isn't just about building bigger and faster spacecraft. It's about building smarter spacecraft. Spacecraft that can adapt to the unknown, that can make decisions on their own, and that can learn from their experiences. We're talking about AI. Imagine a probe equipped with advanced AI algorithms, capable of analyzing data in real time, identifying anomalies and adjusting its course accordingly. Such a probe could explore the intergalactic medium with unprecedented detail, mapping magnetic fields, detecting exotic particles, and even searching for signs of life. The challenges are significant. Deep space presents a harsh environment with extreme temperatures, radiation, and limited communication bandwidth. AI systems would need to be robust, energy efficient, and able to operate autonomously for decades. But the potential rewards are even greater. An AI-powered probe could uncover new laws of physics, discover new forms of matter, and perhaps even answer the ultimate question: are we alone in the universe? The implications extend beyond pure science. Interstellar exploration could also pave the way for new technologies, such as advanced propulsion systems, materials science, and energy generation. These technologies could have a profound impact on our lives here on Earth, leading to new industries and new solutions to global challenges. And then there's the human element. While robotic probes are essential for initial exploration, the ultimate goal may be to send humans to the stars. Interstellar travel poses immense challenges, including the need for multi-generational ships, closed-loop life support systems, and protection from cosmic radiation. However, these challenges are not insurmountable. With advances in technology and a renewed commitment to space exploration, humans could one day venture beyond our solar system and establish a permanent presence among the stars. The legacy of the Voyagers is one of exploration, discovery, and inspiration. They showed us that it's possible to reach beyond our planet and explore the vast unknown. They challenged our understanding of the universe and opened up new avenues of research. As we look to the future, we must build on their legacy and continue to push the boundaries of human knowledge. We must invest in new technologies, foster collaboration among scientists and engineers, and inspire the next generation of explorers. The journey to the stars will not be easy. It will require patience, perseverance, and a willingness to take risks. But the potential rewards are too great to ignore. The future of humanity may depend on our ability to explore the universe and find our place among the stars. Consider the potential for resource acquisition. Asteroid mining is already a field of intense interest, but what about resources found in other star systems? Rare elements? Isotopes with unique properties? The possibilities are almost limitless. Of course, the ethics of such endeavors would need careful consideration. The Voyagers also sparked the imagination of artists and storytellers, inspiring countless books, movies, and television shows. The idea of interstellar travel has captured the human imagination for centuries, and the Voyagers have made that dream seem a little bit closer to reality. This inspiration is crucial. Funding for space exploration relies on public support, and that support is fueled by excitement and wonder. The more people who are inspired by the idea of exploring the universe, the more likely we are to see continued investment in space programs. Further examination reveals that the Voyager probe's golden records, carrying sounds and images of Earth, represent a powerful message of hope and peace to any extraterrestrial civilizations that might encounter them. They are a testament to the best of humanity, our curiosity, our creativity, and our desire to connect with others. The long-term survival of humanity may depend on our ability to become a multi-planetary species. Our planet is vulnerable to a variety of threats, including asteroid impacts, climate change, and nuclear war. By establishing colonies on other planets, we can reduce the risk of extinction and ensure the survival of our species. And it's not just about survival, it's about growth, expansion, and the pursuit of knowledge. Exploring the universe is an inherent part of what it means to be human. It is a way to challenge ourselves, to push our limits, and to discover new things about ourselves and the world around us. Here's what's wild. The data from Voyager continues to be relevant even with newer missions and telescopes coming online. It's a baseline, a historical marker against which we can measure changes in the interstellar environment over decades. That long-term perspective is invaluable. The scientific instruments may be aging, the power source dwindling, but the Voyager's contribution to our understanding of the cosmos is undeniable. They were pioneers, venturing into the unknown and paving the way for future generations of explorers. Their journey may be nearing its end, but their legacy will endure for centuries to come, inspiring us to reach for the stars and explore the vast wonders of the universe. And then the question becomes, what's next? What new missions will build upon the Voyager legacy? Which worlds will we explore, and what secrets will we uncover? What if Voyager's true legacy isn't just about where it went, but what it forces us to become? It's easy to get caught up in the sheer distance, the technological marvel, the incredible images beamed back across billions of miles. But beyond the headlines and the data points, there's a deeper, more profound story unfolding, one about humanity's relationship with the universe and with itself. Consider the sheer audacity of the mission. At a time when computers filled entire rooms and interplanetary travel was still largely science fiction, we dared to launch 2 probes on a grand tour of the outer solar system. We aimed them at targets so distant that sunlight itself is a pale, weak glow. And they worked. They exceeded all expectations, returning data that reshaped our understanding of the planets, their moons, and the space between them. But the data itself is only part of the story. Voyager's journey has also forced us to confront our own limitations, our own biases. The universe, as revealed by these probes, is far more complex and surprising than we ever imagined. The heliopause, that boundary between our solar system and interstellar space, turned out to be a fuzzy, dynamic region, not the clean, sharp edge we had predicted. The interstellar medium itself, the space between the stars, is filled with unexpected magnetic fields and cosmic rays. These surprises aren't just scientific curiosities. They challenge our fundamental understanding of physics, of astrophysics, of the very nature of reality. They force us to refine our models, to develop new theories, to push the boundaries of human knowledge. The implications extend beyond the purely scientific realm. Voyager's journey has also inspired generations of scientists, engineers, and dreamers. It has shown us that anything is possible, that even the most ambitious goals can be achieved with enough ingenuity, determination, and collaboration. Think about the scientists and engineers who dedicated their careers to the Voyager program, working tirelessly for decades to keep the probes functioning and to analyze the data they returned. They faced countless challenges, overcame numerous obstacles, and persevered in the face of seemingly insurmountable odds. Their dedication is a testament to the power of human curiosity and the enduring spirit of exploration. And then there are the artists, writers, and filmmakers who have been inspired by Voyager's journey to create works that capture the wonder and awe of space exploration. These works have helped to share the story of Voyager with a wider audience, inspiring millions of people around the world to look up at the stars and dream of what might be possible. Here's what's wild. Voyager also serves as a stark reminder of our own fragility. The probes are aging, their power source is dwindling, and their communication signals are growing fainter with each passing day. Eventually they will fall silent, becoming silent, sentinels drifting through the vast emptiness of interstellar space. This inevitable end is a poignant reminder of the transient nature of all things, including our own civilization. It underscores the importance of preserving our knowledge, of sharing our stories, and of continuing to explore the universe so that future generations can build upon our achievements and carry on the quest for knowledge. Voyager's golden records, those time capsules containing sounds and images of Earth, represent a powerful symbol of hope for the future. They are a message in a bottle cast into the cosmic ocean, in the hope that one day, someone, somewhere, will find them and learn about our civilization. The long-term survival of humanity may very well depend on our ability to embrace the spirit of exploration that Voyager embodies. We face numerous challenges on Earth, including climate change, resource depletion, and social inequality. Overcoming these challenges will require the same kind of ingenuity, determination, and collaboration that made the Voyager mission possible. Further examination reveals that as we continue to explore the universe, we will inevitably encounter new challenges and new opportunities. We will discover new worlds, new forms of life, and new technologies that will transform our understanding of ourselves and our place in the cosmos. The universe is vast, complex, and full of mysteries. It is a source of endless wonder and inspiration. Voyager has given us a glimpse of this wonder, and it has inspired us to continue exploring, to continue learning, and to continue pushing the boundaries of human knowledge. And then there's the simple, undeniable truth. The journey never truly ends. Even as Voyager fades, its legacy continues to inspire. The next generation of explorers is already being trained, new missions are being planned, and new technologies are being developed. The quest to understand the universe will continue, driven by the same insatiable curiosity that launched Voyager on its epic voyage. Scientists discovered that the data from Voyager will remain relevant for decades to come, providing a valuable baseline for future missions. And the spirit of Voyager, the spirit of exploration and discovery, will continue to guide us as we venture further into the unknown. The implications extend far beyond just the science. Voyager has shown us what we are capable of achieving when we work together, when we embrace innovation, and when we dare to dream big. It is a reminder that the future is not something that happens to us, but something that we create. Want to support future missions? Consider supporting your local science organizations.